Greetings, everyone. Thank you so much for being on time for today's Veolia Water Tech Talk. We're going to begin the broadcast in just a few moments. I'm still seeing a lot of sign-ins here on the attendee list, so we'll just give it another few moments to allow people to log on, figure out their audio, and get settled before we kick off the broadcast. Thanks for your patience, and we'll start soon. Looks like several more people joined the webinar broadcast. Again, we're going to just start in a few moments. There's still a lot of people logging in. There's a lot of people registered for this, so we'll give it another moment or two before starting the broadcast. Thanks again. Great. We're going to go ahead and get started. My name is TJ Wiltz from Veolia, and I'd like to welcome you to today's Veolia Water Tech Talk entitled Hard Water, Hard Problems, Modern Solutions for Water Softening. We have some few slides to get through before we start on the technical portion of our broadcast. Here's some housekeeping slides. You should be hearing me speak now. There are two methods to listen to today's webinar. You could go ahead and use your computer headphones or speakers. If there's an issue with that, there's another option to log on via phone, and you could toggle to that and dial in like you're dialing in for a conference call. With everyone who's logged in, everyone's microphones are automatically muted. And as a reminder, this webinar broadcast is being recorded, and it'll be shared within 24 to 48 hours after the live broadcast. So be on the lookout for it in your email. Now, though everyone's microphones are muted, we want to make this broadcast as interactive as possible. So there's a question box, almost like a chat box on the right side of your screen. If you want to go ahead and log a question at any time during the broadcast, we've reserved some time after the broadcast to go ahead and get through those questions. So go ahead and do that as you see fit. Now, we have a lot of webinars throughout the year that we host live, but we also maintain an extensive library of on-demand webinars, and you could visit our website, veoliawatertech.com, log on there and watch any webinar that you see on there at your leisure. Now, if you're looking to have this webinar count for continuing education, we're going to issue a participation certificate, and that's going to come in your email inbox 24 hours after the live broadcast. Now, after the broadcast, you'll be taken to a place to do a short survey. We have a quick survey. It only takes about 3 minutes to do. And anyone that takes that moment to go ahead and fill out that survey, we're going to issue a $25 Amazon gift card that we'll raffle off for everyone that did that survey. Now, a little bit about Veolia. We're within the WaterTech version of Veolia. In that group, we focus on 4 key main areas. That's projects, products, technologies, services, and chemicals. And then we support various industries across the North American market here: food and beverage, pharma, pulp and paper, mining, oil and gas, chemicals, and also municipal. Now we're going to get into our technical portion of our webinar, and we have 2 panelists that are joining us here today. The first one that you'll be hearing from, his name is Harrison Fowler, and he's a specialist within our softening technologies as a sales engineer. He brings over 10 years of water and wastewater industry experience within Veolia, spanning everything from pilot engineering, field service, applications engineering, product development, sales, and also supporting municipal and industrial markets. Specifically, he's the sales manager for softening and oversees the equipment, sales, and product management for the various softening technologies, many of which you'll hear about today. And his experience is full life cycle from design to execution, and he supports his clients readily with making sure those projects are successful from conception to execution. Also with us today is Brian McGovern. He is an industrial business development manager, and he brings over 20 years of water and wastewater industry experience. And then he's been with Veolia for most of those years, again, with an impressive career spanning everything from process engineering to business development to field service as well. He oversees Veolia's equipment for water treatment. He oversees Veolia's water treatment portfolio, including Annex colonists, moving bed biological reactors, biothane anaerobic technologies, and many, many more. So again, he also is experienced in taking customers' challenges and making sure that the technology and equipment goes ahead and meets those expectations for our clients. So without further ado, I'm going to hand over the webinar to our first panelist, Harrison. And Harrison, are you with us today?
I am. Thank you, TJ.
Thanks, Harrison.
Yeah, so again, my name's Harrison Fowler, specialize in softening technologies and sales manager across the U.S. municipal and industrial markets. And a little agenda for you today, what we're going to be talking about, just kind of a background around hard water, hard problems, kind of an overview of the existing core softening technologies that are available in the municipal and industrial markets, and then talking a little bit about pellet softening, softening and the circular economy, a few case studies, and getting started with a softening project. So hard water scope and challenges. So as you can see on the map, across the United States, there are large swaths of area in multiple regions of the country that are classified as hard, very hard, and extremely hard in grains per gallon. These regions of the country, if you will, represent a large part of the core softening market and the reason for softening, whether that be at the raw groundwater stage, hard surface waters that have contact with limestone, you know, and really anything in between, groundwater under the influence, the list goes on. But as you can see, again, 85% of the country has hard water. So this is a widespread issue, a little bit of different issues depending on the market that we're talking about, but essentially all the same problem. So some of the common risks created by hard water, as you can see from the photos, really scale and corrosion are the two that come to mind when you think about softening, when you think about hard water and how softening impacts that. That can also lead to things like reduced efficiency within utilities infrastructure, whether that's piping, valving, other processes up or downstream process, piping and valving, if you will, in industrial spaces, and the same in municipal. More so on the municipal side, taste issues, high TDS can contribute to complaints from the ratepayers in regards to taste. And on the industrial side, product quality is also impacted here. So everything that we're going to be talking about today is sort of geared towards addressing some of these challenges that both municipal and industrial markets see. So common technologies to treat hard water. As you'll see on this slide, you really have four methods of softening, if you will. Common softening technologies in the U.S. Traditionally, the U.S. market has heavily relied in all market sectors on cold lime softening. It was adopted around 100 years ago and really represents a large market share of softening technologies across both markets. Ion exchange is one that is utilized heavily in the industrial market, somewhat on the municipal side. We also see on the municipal side quite a bit of point-of-use softening, so in-home softeners, if you will, that can create their own set of challenges down at the wastewater plant and other areas. Nanofiltration, RO, definitely membranes have their place in the softening market, particularly nano and reverse osmosis. That is primarily used in the industrial market, but we see quite a bit of growth on the municipal side as well in the membrane space for challenging to treat waters, brackish waters, things of that nature. And then kind of followed into additional softening technologies. Both of these are still considered precipitation-based technologies, such as lime softening. A little bit different way to do it, small footprint, high rise rate, more specialized niche treatment, if you will. But at its core, these four softening technologies really represent the current state of the market and how we can approach softening. So the one that everybody knows probably the most in these markets is cold lime softening, chemical process using a clarifier. Lime is injected either as a flaked lime or a ultra high purity hydrated lime system. Very cost effective on the equipment side. You can treat a large volume of water, groundwater, surface water, if you will. You can remove multiple contaminants such as calcium, magnesium, silica, sulfate, and other various compounds. The challenges with this process in particular would be around the residuals management, waste management, if you will. You generate a sludge. That sludge has to be handled, thickened, dewatered, and hauled. Traditionally, sludge is disposed of either in landfills or land application, but as the market grows, lime has gotten more expensive. Residuals management has also gotten more expensive, both on the handling and the hauling. And it can be, in certain situations, a difficult process to control. Just a little PSD of sort of traditional lime softening. You'll note you have aeration in some cases, solid contact clarifier where lime is injected. Typically on the municipal side, you'll see a filtration step followed by storage, but then you also have an element of, again, that waste residuals management, thickening, solids handling. In this particular case, a centrifuge was used, but presses, there's a lot of mechanical equipment that goes along with the core softening process. So overall, a pretty complicated PFD to achieve softening. Ion exchange is the next traditional softening technology. Again, you heard me mention that it is used at scale in the industrial markets and also municipal markets in some settings. Traditionally, these are pressurized vessels with a resin that is specifically made for calcium and magnesium removal. Typically, it is used with a sodium or potassium ion regeneration step, where you make down a brine, you regenerate the media, the resin media, every so often to maintain media integrity and consistent softening. Challenges with these systems include the resin regeneration and cost and or replacement over time. The brine that is generated by this process is traditionally pretty difficult to handle. When discharged to sewer or other places, it is a very heavily chloride loaded side stream, if you will. And then it's traditionally pretty specialized to softening. So if you have a large amount of other contaminants, they can cause a detrimental effect to the resin within the vessels. Nanofiltration, reverse osmosis membranes, if you will. I'm sure everyone on this call has spent some time around membranes at one point or another, but it is a physical separation process in that water is pushed under high pressure through a membrane. Certain ions are separated away from others. Clean, soft water, if you will, passes through these membranes, while other hardness, ions, metals, and dissolved solids are rejected into a membrane stream. These are easy to operate. You have a wide range of contaminant removal, and you have very effective hardness removal that could allow you to run blends, reduce the amount of waste, etc. Some challenges around membranes include high energy costs. Again, that membrane fouling cleaning replacement based on the water that you are treating. Potential pre-treatment steps involved going to membranes, whether that's UF, or other separation pretreatment technologies. And again, you still do have an element of a liquid waste stream, continuous waste stream that is very concentrated that needs to be disposed of. The methods of disposal include side stream treatment of that reject stream, hauling and or discharge to sewer.
Well, at this time, we're going to welcome our next panelist with Brian McGovern, who will join us to talk a little bit about high rate softening. Brian, are you with us?
Yes, I am, TJ. Well, good afternoon, everyone. As Harrison had mentioned previously, we talked a little bit about cold lime softening. And here at Veolia, we look at optimizing technologies in order to reduce footprint and capital costs for our customers. And so on high rate hardness removal technologies, we have quite a few offerings and a couple of different clarifier options that we're able to employ, such as our ActiFlow clarifier, our Densator clarifier, as well as our MultiFlow clarifier. And the benefits of these is, again, compact footprint. We're able to have high loading rates. Surface loading rates are increased as compared to a traditional solids contact clarifier. With these clarifiers, the tanks and the overall clarifier system have an integrated coagulation, flocculation, and settling tank integrated into each of the clarifier designs, which basically helps us to control the injection and mixing of the proper chemistry needed for cold lime softening. And it produces a flock that is easily settleable in the clarifier section. And each of these clarifiers are provided with a complete detailed control panel with fully automated operation. The first clarifier that we offer through Veolia is our ActiFlow clarifier. This is a ballasted clarifier where we use sand as a ballast, which is recirculated to a hydrocyclone and is then injected into the flocculation tank. So for lime softening, we have an initial softening tank where raw water enters, and we have turbine mixing with lime and caustic soda possibly added for raising the pH and introducing the calcium. And then we have a coagulation tank where we will add possibly a small amount of ferric chloride to introduce a coagulant. And then the flocculation tank is where that micro sand combines with polymer that we inject to basically produce a dense flock, which then settles into the settling tank or the clarified water tank. And the effluent water then flows through lamella tubes and then flows out to a common effluent for the clarified effluent water. And typically on the backside, depending on pH requirements, we can add a acid injection so that the actual operating pH coming out of the clarifier can be close to neutral so it can be discharged. This is just a cross section of one of our other clarifiers that we're able to offer through Veolia. This is our Densator clarifier. Again, this is one clarifier with multiple tanks integrated, where we have a rapid mix tank where we're able to add lime as well as coagulant. It then enters into our reactor tank, and that reactor tank has internal sludge recirculation. And then with our Densator clarifier, we also have recirculation from the clarifier section. So we have internal sludge recirculation and external sludge recirculation to produce a very thick and dense flock. Typical rise rates for this clarifier are in the 8 to 12 gallon a minute per square foot for softening applications. And again, the clarified water travels up through settling tubes and out to the effluent. A thickened sludge settles in the bottom of the clarifier. Under softening applications, the sludge can be anywhere between 3 and 10% solid, so it's a very thick sludge that is produced. So there's no need for additional thickening. The sludge off of these clarifiers can go directly to a plate and frame filter press, typically under softening applications. Then we also have another version, which is our multi-flow clarifier. The big benefit, this basically operates very similar to the densator. This offering, the multi-flow, we have standard configured clarifiers that can be manufactured in our facility in Canada and delivered directly to the site. So these are basically packaged clarifier units that can be provided for a softening application. And just to show some comparisons of the performance of each of these systems, again, each of these clarifiers are having a high maximum rise rate or maximum rising velocity. With our ActiFlow softening, with the addition of the ballast and the sand, we're able to reduce the overall footprint because the overall rise rate is typically in the range of about 20 to 30 gallons a minute per square foot. A traditional solids contact clarifier could be anywhere between about 0.5 and 1 gallons per minute per square foot. So again, it's reducing the footprint. The sludge concentration, basically the sludge that is recirculated to the hydrocyclone combines and is then sent off to the solids dewatering applications. And with our clarifier, we see reduced effluent concentrations, typically in the range of less than 5 to 10 milligrams per liter of TSS, which could be equivalent to less than 1 or 2 NTU. And also for hardness removal, we're typically seeing less than 35 milligrams per liter of calcium, as well as less than 50 milligrams per liter of magnesium. Our densator and multi-flow options are a little bit reduced in their rise rates. And so really, depending on influent water quality, we're able to select the appropriate clarifier technology. Typically with higher solids in the influent water, this will push us to utilizing either a densator or multi-flow softener with maximum rise rates of 12 gallons a minute per square foot. And with that, with the higher solids coming in and the thickened sludge, we have significant sludge concentration of 50 to 100 grams per liter in the sludge. Again, 5 to 10% solids concentration, and performance is nearly equivalent to the ActiFlow as well. And so just to show a little bit, this shows kind of a conventional precipitation softening or a solids contact clarifier, which is around 0.8 gallons a minute per square foot. In yellow, it shows basically the footprint of our densator and multi-flow softener applications, which is designed around 12 gallons a minute per square foot. And then again, reduced in the blue is the overall footprint of our ActiFlow softener, which is in the range of 30 to 32 gallons a minute per square foot. And again, the cold lime softening up top kind of shows a traditional solids contact clarifier that Harrison had touched on earlier. And then below shows some of our ActiFlow or multi-flow package units that are able to be provided to a customer for a softening application. One case study, one that I'd like to touch on regarding a softening application is our Lodi Energy Center, which is out in Lodi, California. This was a plant that utilized our densator clarifier for softening. The Lodi basically Energy Center was looking to expand from 50 megawatts to 300 megawatts. And based on that expansion, they were needing additional softened water for the process. They were required approximately 2.6 MGD or 2.6 million gallons per day. And this facility was basically utilizing municipal wastewater from a local wastewater treatment plant. And basically, we're looking at reducing the overall hardness as well as silica in the water so that it could be used at the facility. This design in this plant was using a combination of both cooling tower blowdown as well as the effluent wastewater from the municipal wastewater treatment plant. In overall, approximately the design of the system is for about 2,000 gallons per minute. With a combined hardness and calcium and magnesium and silica requirements. And based on the magnesium in the influent water, it's significantly reduced. And so supplemental magnesium for the overall process to remove silica is required, and we used magnesium oxide as an alternative to provide supplemental magnesium to facilitate the absorption of silica. So this is just an overview of the process flow. We take the treated, tertiary treated water. They go through the densator clarifiers. There is one common rapid mix tank, and there's 2 clarifier trains that were provided. The effluent water is then sent either to plant service water or is then sent to a DMIN system for UF, RO, EDI for boiler feed water, as well as the effluent from the clarifiers is also sent to basically evaporative coolers. And again, as I mentioned, the chemical addition, we're adding lime. That lime is then removing the soluble calcium and removing the soluble magnesium. We had to add supplemental magnesium in the form of magnesium oxide to remove silica, added a flocculant, a polymer to enhance the suspended solids removal, and added sulfuric acid for final pH adjustment. The picture up top just shows the effluent water quality coming off of the densator. You can see the inclined lamella tubes for settling flows over to V-notch weirs, and the effluent is then collected and goes to a storage tank. The results from our performance test that we had performed, we had to meet certain criteria. We had to meet calcium less than 60 milligrams per liter. We were below that requirement at 59. The magnesium less than 5 milligrams per liter. We were at less than 4.1. Silica removal less than 15 milligrams per liter. With the addition and supplemental magnesium addition, we were able to meet that by providing less than 10 milligrams per liter silica. Suspended solids guarantee, we had to be less than 5 milligrams per liter. Our guarantee was performance showed that we were less than 2 milligrams per liter, as well as a iron and phosphate removal guarantee that we met pretty comfortably. And now I'll hand it back over to Harrison, who's going to focus on one of our other high rate technologies, which is our pellet softening Actina process.
Thanks, Brian. I appreciate it. So Actina pellet softening at its core is a precipitation-based softening technology where we use caustic in the majority of our applications, sometimes lime if there is a specific TDS issue that we are looking at. But essentially, we are using a upward flow fluidized bed reactor with a seed material of either silica sand or pure calcium carbonate material. We fluidize that material within the column. We introduce a pH adjustment chemistry in caustic soda or lime, and we precipitate calcium, iron, and manganese out of solution and onto pellets. This particular process is very unique in the fact that it has an extremely small footprint. It runs at roughly 40 gallons a minute per square foot, and it produces a solid waste. Within the reactor itself, there are no moving parts, no mixers, or anything of that nature, and we are simply using the seed material, which is surface area, that's available within the fluidized bed to precipitate calcium out of solution and form calcium carbonate pellets. The one thing to note here about this process specifically is that because we are able to produce a solid waste product, there is no dewatering necessary for that waste. We are able to discharge it from the reactor into a holding area that has screens in it, whether that's a bin or a hopper. The water drops out and you're left with a 95% dewatered waste product upon discharge to the waste area. Just a really quick PFD of what a Actina pellet reactor plant would look like. If you can remember a few slides back, the PFD of a lime softening plant, this was really sort of a direct comparison to that, in which you have a well going straight to a pellet reactor. We have a stabilization basin to inject CO2, stabilize that water, and get down to a neutral water balance, filtration, storage, and transmission. Your waste product is simply blown to the pellet hopper and hauled off. The basics of pellet softening. So again, you heard me mention the fluidized bed reactor, which you can see in that column. We're pumping water under pressure into the bottom, going up through a nozzle deck that I'll show you in the next slide, fluidizing that bed of seed material, whether it's silica sand or calcium carbonate seed, and we are precipitating calcium carbonate onto that seed and forming the pellets. So you can expect a growth factor of 3 to 4 times what your seed size is into a mature pellet. And with that crystallization and pellet formation, we are also able to trap iron and manganese there as well. So it makes it a pretty effective way to remove calcium, iron, and manganese from a water source and produces a nice solid waste that really is more of your sustainability-driven initiatives. That's one of the biggest comparisons that we've seen to other types of precipitation softening is managing that waste product. So just a quick overview of what's going on in the reactor and the inputs and outputs. Again, you got hard water coming in, going up through the flow strainer deck. You've got your expanded bed of seed and pellets. We're introducing pH adjustment chemistry in right above the nozzle deck, precipitating calcium, iron, and manganese out of solution and forming those pellets. And then you've got your seed makeup in, which will be your fresh seed, sand, or calcium carbonate, and then your pellet extraction or your blowdown out. That is controlled by mass balance that we'll touch on in a few slides. So talking about flow distribution, really from a pellet softening perspective, flow distribution is key for 2 things. It's even distribution of the flow coming into the plenum, ensuring that you have consistent flow across the cross section of the nozzle deck, and also to distribute chemistry. And I'll touch on that on the next slide. But if you notice here, we have a sort of a breakdown of our nozzle deck, and you can see water going into that plenum, coming up through these nozzles that you see a cutaway view of. And then from there, we're using that rising turbulence, if you will, to pick the bed off the floor, keep it in fluidization or suspension, and then introduce chemistry in the base. When you talk about pellet softening, the nozzle deck is really the key to the entire process. It's in a sense, it's the beating heart of the process. Talking about chemistry, so you heard me touch on caustic. That is the chemistry of choice that we like to use from a design perspective. Really, what that allows you to do is maximize the rise rate through the reactor. It allows you to make those reactors smaller and fit into very tight footprints. The caustic reaction in hard water is very fast and efficient, so it allows us to pull 90% of calcium out or more in certain situations. And we use a couple of design points around that as well. So we have a dilution water that we blend with caustic. We bring the blended caustic and the carrier water to the injection point under pressure and high flow, and it allows us to inject that pH chemistry, if you will, disperse it and mix it evenly at the base of the reactor above the nozzle deck, and really drives the precipitation reaction. So within that, we have a removable injection device that we call a chandelier that we lower in from the top down, and that's where we're sending the chemistry into. And what that allows you to do is actually keep a spare injection device or chandelier on the deck of the process and swap that out. So when you talk about maintenance and keeping the process going, by being able to remove the injection device, it does not force you to take the reactor down, empty the reactor, fully clean it before you swap that out. So that is something that we've developed over time, and definitely with that plus the nozzle deck, that is really the key to the entire process, that even flow distribution, even chemistry distribution, and ultimately a even precipitation reaction and pellet generation. So talking about seed management, if you will, whether that be sand or calcium carbonate, it really is driven by the size of the system and the demand of seed per day based on that mass balance that I mentioned. So anything from a hand-fed small adductor, bulk back feeder, and mid-capacity systems, or large systems where they require hundreds of pounds of sand a day, and we use an automated silo. We really manage that effort through a combination of operator strategy and control strategy. We also include with our base offering a seed washer where we make a wetted slurry of that sand or that calcium carbonate material, and then that is washed to remove all the fines, keep turbidity consistent across the effluent discharge of the reactor, and ultimately send that wetted slurry from the washer to the process. Also, just to mention, typically post-precipitation softening, no matter what process it is, there will be some element of recarbonization or post-softening pH control. In this particular case, most of the time in the municipal market, we see that being done with carbonic acid or sulfuric acid. In the industrial space, more so sulfuric acid, citric acid can be used, but typically that's what we see. So talking about managing the pellet bed, the system uses PLC-based controls on valves. We watch the pressure differential in both the intake plenum and the base of the reactor. As the bed grows, the pellets grow in size, the bed gets heavier. It exerts more head loss against the inlet of the intake plenum. The PITs track that pressure increase, and we use that coupled with a function of time to introduce blowdown strategy into the system. And from there, it's managing the bed, where you introduce a certain amount of sand every day, once per day, twice per day, depending on how the reactor is operated, and you blow down a certain amount of pellets in pounds per day. And just quickly touching on pellet handling, again, you can send these pellets to a roll-off dumpster with screens in them, or send them to elevated hoppers, as you see in the picture to the left. The water free drains out of the pellets. You're left with a 95 to 98% dewatered waste pellet that you can then haul off, land apply, or any other core functions that you can find to use with the pellets. So touching quickly on the pellet reactor expected performance, again, it is primarily a calcium removal process, but as you can see, we can also achieve significant removal percentages in iron, manganese, along with some sulfate and some fluoride removal. The color of the pellets is driven by the amount of constituents present in those pellets. So all calcium, you're going to see a nice white finished pellet. If you have a bunch of iron, obviously you'll see pellets similar to vial A with that nice dark rust color. And then if there's a bunch of manganese present, it will show up as a tannish grayish color. Just quickly on waste for the pellets themselves, we do have one municipal source that I'll touch on that uses pellets for agricultural calcium supplement. Other sustainability initiatives include fertilizer, building products, also public works use as well. And then other examples of Actina pellet reactor applications, treatment for RO brine, softening that brine, treatment for nano brine, sort of the same premise. Really, we're looking to remove all that calcium out of that source and potentially be able to introduce it to another process for reuse. TJ, if you just want to, yeah, there we go. So this is just a quick touch on what the reactor looks like under operation. You can see the chemistry going down to the base of the hoses. You can see the fluidized bed rolling, and you can see the clarified effluent, softened effluent, if you will, rising to the top. Very similar video, different installation, again, highlighting that fluidized bed, that even mixing, that even distribution, if you will, of the pellet bed and the seed material. So quickly touching on a flagship installation we have out in Denver, Colorado. South Adams County is roughly a 13.8 MGD drinking water facility. They have somewhere in the range of 350 to 400 milligram per liter of total hardness coming in. This particular plant was driven by the need to soften. They were not softening prior to introducing this expansion. And really, this was a combination of the utility, the ratepayers, the district, and the engineer to come up with a very comprehensive solution to address their hardness issues. And this process, by far and away, was the cheapest in both CapEx and OpEx to achieve their goals. Key points to note here: relatively consistent influent hardness, as this was a groundwater source, very consistent effluent hardness, if you will, very targeted goals in terms of effluent hardness, but again, no liquid waste, and the ability to repurpose their waste product drove the decision making within this project. Just a couple of photos and videos there. If you want to take a virtual tour of that facility, please scan this QR code and you will be able to do that.
We'll just give it about 5 seconds for people to take out their phone and take a picture of that QR code, because it's really good to really experience that drinking water facility.
So another industrial application, Actina was utilized in pre-treatment for processed water makedown. Essentially, we were taking Actina, treating the water source coming into the facility, removing all the calcium out of that stream, and then sending it downstream to other industrial processes. And as you'll note, really the goal here was two things. It was processed water makedown for the various components of that particular facility, and really sustainability in reducing the amount of liquid waste being generated by these water treatment processes, and ultimately trying to get all that calcium into a solid form before it ever made its way to the plant. So quickly, just getting started on a softening project. couple of things to note here. Obviously, identifying your source water and treatment needs would be the first step. Determining the available footprint that you have, whether that be for a new process train, new plant itself, or an existing expansion of existing treatment. Really taking a hard look at the TDS breakdown of your feed water stream and understanding what is present. That drives the decision making around what technology to use, and identifying those problematic constituents can definitely lead to a more optimized softening solution for your clients. Again, 4 key takeaways. The primary methods of softening: ion exchange, lime softening, RONF, and pellet softening. Within precipitation softening, you do have lime softening, pellet softening, along with your high rate solutions in ActiFlow, Multiflow, Soft, and Densator. Pellet softening is unique in the fact that it only removes calcium-based hardness, but it does produce that solid waste, so it can be a highly effective option when coupled with other treatment processes. Raw water makeup and effluent targets are always going to drive your selection of the softening technologies. And at the forefront of sustainability, CapEx, OpEx, sustainability, what are you going to do with the waste? How are you going to handle that will be the key in selecting the appropriate technology for the application.
Great, Harrison, thank you so much. And also thank you to Brian for sharing those, all that experience and that case studies and some breakdowns on all of those technologies. Quite an expansive overview of the options available to the marketplace for softening. As mentioned earlier in today's webinar, we have allotted some time for some questions. We've got quite a few questions that came in. So we're going to try to get through those. Also, reminder, if you haven't done so and you do have a question, feel free at any moment to go ahead and enter that into the question box, and it should be attached to your GoToWebinar panel on the right side of your screen. A few people asked this in a few different ways, but maybe we'll try to ask it again. There are so many options when it comes to softening, ones that have been used for many decades, and also some new, more novel approaches to softening. I guess maybe you could take just a few moments and go ahead and talk through what is the right fit for the application for the various technologies that we have. So I'll hand that question over to Harrison. Harrison.
So in terms of selecting the softening technology, as I mentioned, really looking at your raw water makeup and determining what part of that TDS is problematic. Traditionally, calcium causes major scaling problems, right? So whether that be piping, valving, boiler, feed house, cooling towers, the list goes on and on and on. We talk to a bunch of clients and they all have similar issues around calcium. We need to get it out and we need to stop it from making its way to places that causes significant issues in regards to maintenance and operations over the course of the year. So knowing that, coupled with what are your options for your waste or your residual stream disposal. Every market is different. Some markets have the ability to send liquid waste to somewhere else to have it treated. Some markets have to haul that off because there is no on-site liquid waste disposal option. So I would say looking at your TDS breakdown and understanding what's present and what is problematic, coupled with your waste disposal options and ultimately what your treatment goals are, is really going to drive the decision making in what we would recommend in selecting a softening technology. And there is not always a straightforward answer. It could be you have to take out different constituents in different stages of the same process treatment train. And again, it ultimately comes down to, obviously capital expenditure, operational expenses, any sustainability initiatives that have been identified, like reducing liquid waste, like playing nice with your local municipal water and wastewater plant. All those factors will contribute, if you will, to the decision making around selecting the appropriate softening technology.
Great, thanks for that. And just an added comment to that is that It's might be difficult, but what we've done in many cases is looked at all of those project specifications and try to find that right tool for the job. So feel free to reach out to Harrison or Brian or myself, and we can connect you with the right technical group to go ahead and help you do that evaluation when it comes to figuring out the right tool. Another question, it's going to be, these came in during the high rate clarification portion of the softening presentation. So for Brian, the first question I have is talking about scaling. Calcium carbonate scales tend to be difficult to remove from surfaces. Does the precipitated calcium carbonate on the ballast material come back off sufficiently in the ballast cleaning step? So maybe you talk about that and how we try to mitigate scaling within those reactors and prevent excess scale.
Yeah, sure. So typically with our clarifier, our materials of construction are typically going to be either epoxy coated carbon steel for the package clarifiers, but the mixers and the internal components are all going to be typically manufactured in either 304 stainless or 316 stainless, which is going to be limit the amount of scale buildup. With a couple of our clarifying options as well, we are able to have valves that reduce the water within the clarifier tank, reduce it below a certain level so that, for instance, we could hose off and clean any of the lamella tubes. And so that's just a manual operation that's done to ensure that there's no buildup of any solids on the lamella tubes and things like that.
Great. Thanks for clearing that up. Another question, and it's probably related to the Lodi case study, but it was talking about silica removal. And the question is about temperature adjustment to make sure to achieve silica removal with MgO. Can you talk about how sensitive the lime softening process is with temperature in that case?
Yeah, so with typical cold lime softening, obviously you don't need to worry about the temperature as much. You can look at hot lime softening, that's another option. But then you have to look at different materials of construction and things like that. For instance, those lamella tubes in our standard offering are typically provided in plastic or FRP, which are going to be temperature sensitive. So for hot lime softening and things like that, you may look at other materials of construction. Regarding silica removal, really in cold lime softening, it's really based on combining and basically absorbing with the magnesium ion that's precipitated out. You will get better efficiency and better removal at slightly higher temperatures. But again, it's going to be really mainly dependent on how well you're actually precipitating the magnesium, because it's kind of a co-precipitation process with silica removal.
Excellent. Switching gears a little bit to the pelletized reactor Actina. A question came in for you, Harrison, and this is, does the Actina use Spiractors? Maybe you comment on that.
So Spiractor is one of the older type of pellet reactor technologies, if you will, that has existed in the U.S. for probably 30 to 40 years now. That type of reactor was specifically designed to run on lime. It does use a silica seed material as surface area to precipitate calcium too, but that's really, in terms of comparison between Spiractor and Actina pellet softening, that's really the only similarity, in that it uses a similar seed material and the same basic premise to use that surface area available made by the seed material to precipitate to. Actina does not use tangential flow, vortex flow, if you will, to pick the fluidized bed up off the floor of the reactor. And there's some inherent design differences between the two. It's really, I would say Actina is more of an evolution of the pellet reactor in general, the pellet reactor technology in general, over the last 50 plus years of use in Europe. And there are some significant design changes from the old Spireactor versions, which are large cones that are set on feet that run at a much lower rise rate, and again, run typically on lime. So while the premise is similar, it's a completely different type of reactor and method to how we approach deploying pellet softening as a technology.
All right, and continuing with the Actina, another question came in about plant scale size. Can you talk about sort of the range that this technology could be applied in terms of flows?
Yes, so we have the ability to build, taking a step back, our core material construction for Actina pellet reactors is 304 stainless steel. We fabricate those in the United States, and we can build them in any size up to about 5 to 6 MGD per tank. In terms of a larger picture flows, large flows, if you will, most Actina plants that are going to use prefabricated reactors will cap out around that 25 to 30 MGD range. We will obviously have 5 or 6 larger reactors in that configuration. From there is the option to go to concrete and do larger reactors and treat much larger flows. At this time, we are more focused on the prefabricated stainless steel tank route because it affords the end user the ability to get more of a turnkey system with not as much earthwork and concrete work done at the site before the tanks are brought and sat and bolted and plumbed into place. That's not to say that it cannot be done at a much larger scale. We have looked at multiple applications where we are north of 100 MGD, 150 MGD, if you will. And when that situation presents itself, that would be more of your hybrid concrete stainless construction, in-ground, in-place tanks, if you will. Again, on the industrial side, we primarily would lean towards using prefabricated tanks, whether it be for raw water treatment, for some sort of side stream, waste stream treatment, if you will, reject stream treatment. Again, you heard me mention touching on RO and NF reject stream treatment for softening, TDS removal, if you will. So we do have the ability to fabricate them in just about whatever configuration that we want.
Excellent, excellent. Thanks for breaking that down and sharing the flexibility of that particular technology for softening. Well, we are just about at time for today's webinar broadcast. I just want to remind everyone to go ahead and fill out that survey right after the webinar, right after you exit. That'll help us improve these broadcasts, and also to figure out maybe what topics you're interested in the future. So that'll be greatly appreciated to go ahead and fill that out. Just one other note, someone put a question to getting that barcode up again on the screen. I'll email that to the person that asked, but also the recorded version of this webinar will be sent tomorrow about this time. So go ahead and look for that recorded on-demand version where you could rewatch today's broadcast just in case you missed anything. And lastly, just want to put some contact information up on the screen. There's the emails of our panelists today, Harrison and Brian. So if you want to jot those down, go ahead and you could connect with either of these panelists about the various softening technologies that they presented today. So this will conclude today's Veolia Water Tech Talk. I can't thank everyone for spending an hour with us today to learn a little bit about how to mitigate hard water with various solutions that exist. And just want to also thank both of our panelists. I'll thank Harrison and Brian for taking the time to prepare for today's presentation, and more importantly, sharing their decades of experience with us on this particular topic. Obviously, it's a big problem, and it's just good to know that there are multiple solutions that we could employ to mitigate those issues. So really great time today in what you presented. So without further ado, we're going to conclude, and if you have any questions, please do not hesitate to reach out. Thank you all, and have a wonderful day.